Hello everyone, today we'll talk about the IV characteristic of the MOSFET, in this case it's a MOS, and how the gate voltage controls the transistor current from the drain to source. Gate voltage, drain to source. And let's see how it works. So basically there are several phases of it. So we can draw the IV curve. Let's make this one IDS, which means the current coming from the drain to the source. Make the x-axis VGS, which means gate voltage minus the source voltage. So in this case, it's the same thing as VG. But for other scenario, when this one is not grounded, so it's VGS. So the first thing is when the VGS, there's a threshold voltage of the MOSFET. For different MOSFET, different threshold voltage. So when the VGS is less than VTH, the transistor is off. So there will be no current flow. Actually, take it back. There is some current flow. There is some leakage current. And if you switch in the IDS in log scale, you will see there's actually quite some current flow actually. But in this case, we can consider it's off. So there will be very little current, like minimum current. We can consider no current flow. And when the VGS is greater than VTH, then there will be current flow. Then the transistor is on. Then there will be current flow. And the current IDS will increase as the VGS increase. But increase to a certain point, it will no longer increase. It will reach its maximum value. So in this case, let's draw it. So initially there will be, let's consider this point as VTH. So initially there's no current flow or little current flow. At this VTH, it will turn on the transistor, so there will be the current flow. It will be increase. Yeah. So that's the VGS versus IDS. But actually, there are two scenarios when the transistors are on. The first one is when the VDS is less than VGS minus VTH. This one is in the trial region, which means the VDS is no, which means the IDS is directly proportional to VGS. So the increase of gate voltage, the IDS will increase. Linear region, we also call it linear region or trial region. The second part is when the VDS is greater than VGS minus VTH. That's the most important scenario. We call it saturation region. At this time, that IDS will stay at a constant. And no matter how you increase the VGS, IDS will stay at a constant. But in reality, it's not a constant. It will change a little bit, increase a little bit. And we want to keep it as constant, but it's not ideal world, ideal design, so it will change. Let's draw the IV curve. So this one will be IDS, but in this case, we will use x-axis as VDS, because VDS is a determinant factor of whether it's in triode or linear region. So when the VDS is less than VGS minus VTH, you will see the current is increasing like this. And after it reaches the point, it will stay as a constant. But actually, in reality, it's not. So this region, we'll call it as triode. And this region, we call it as saturation. And in the trial and the current, there's equation of the IDS, which is IDS will equal to mu NCox W over L VGS minus VTH VDS minus 1/2 VDS square. So that's the current equation. And the most important equation is actually ID max, IDS max. The maximum current is at the saturation region, so we call it saturation current. So it's ID ID saturation. So equal to this one is very important. You remember it for interview. 1/2 mu n Cox W over L VGS minus BTH square. So this is a very important equation to calculate IDS. So mu n, say mu n just constant. Cox is the capacitance per thickness unit length. W and L are the width. The W is actually the width of the metal. No, the width of the diffusion, and the length is the length of the effective poly or metal in the device level. Like if we draw the cross section, this is a cross section. N plus, this one be P plus, P substrate. This is a gate, this is a drain, this is a source. So in this case, this will be the length L. And you have a diffusion. So these are the diffusion. So this is the W and L for this equation. Yep.